What specific problem does your proposed decoupled reasoning and proving framework aim to solve within the automated theorem proving domain? Can you articulate the limitations of existing approaches that your method addresses?
The proposed decoupled reasoning and proving framework aims to bridge the significant gap between informal reasoning capabilities of large language models, LLMs, and the formal proof generation of automated theorem provers, ATPs. Existing approaches, such as DeepSeek Prover v2 and Kimina, tightly couple high-level reasoning and low-level proof generation within a single model, which constrains their reasoning potential and leads to suboptimal performance on complex problems. This design flaw results in a reliance on brute force tactics and a degradation of intrinsic mathematical reasoning capabilities due to the reinforcement learning with verifiable rewards, RLVR paradigm, which incentivizes models to maximize success rates rather than develop creative problem-solving strategies. By decoupling these processes, our framework allows a specialized reasoner to focus on generating strategic lemmas, while a dedicated prover verifies these lemmas, thus enhancing the overall efficiency and effectiveness of the theorem proving process. This separation not only improves the quality of reasoning, but also enables the integration of verified lemmas into the final proof construction, addressing the limitations of current models that often ignore pre-proven facts.
How does the proposed method or algorithm work? Please illustrate it step by step, detailing the roles of the reasoner and prover modules, along with the stages of sub-goal generation, verification, and final proof construction.
The proposed method operates through a decoupled framework consisting of three main stages: sub-goal generation, sub-goal verification, and final proof construction. In the first stage, the reasoner, a powerful large language model, LLM, generates strategic sub-goals or lemmas based on the theorem at hand, focusing solely on producing formal statements without proofs. This allows the reasoner to leverage its strengths in high-level mathematical insight and creative problem decomposition. In the second stage, the generated lemmas are passed to the prover, specifically DeepSeek Prover v2, which verifies the logical soundness of each lemma by attempting to prove them independently. A lemma is retained if at least one proof attempt is successful, ensuring that only verified lemmas proceed to the next stage. Finally, in the third stage, the prover uses the verified lemmas to assist in constructing the proof for the main theorem. By incorporating these pre-proven lemmas into the context of the original problem, the prover can simplify the proof task, transforming it into a more manageable assembly of the final proof using the verified components. This structured approach effectively bridges the gap between high-level reasoning and formal proof generation, enhancing the overall problem-solving capability.
Can you provide a simple yet illustrative example demonstrating the inner workings of your proposed algorithm, particularly how the reasoner generates sub-goals and how the prover verifies them?
In our proposed algorithm, the reasoner first generates strategic sub-goals by identifying key lemmas that can simplify the proof process. For instance, when tackling a complex problem, the reasoner might isolate fundamental properties of a function, such as deducing that a function satisfies certain identities. This is done without generating full proofs, focusing instead on producing formal statements of potential lemmas. Once these sub-goals are generated, they are passed to the prover, which verifies each lemma independently. The prover attempts to find proofs for these lemmas, and if at least one proof attempt succeeds, the lemma is considered verified and retained for use in constructing the final proof of the main theorem. This decoupled approach allows the reasoner to explore creative strategies, while the prover ensures formal correctness, effectively streamlining the proof process.
What are the theoretical or practical benefits of your decoupled approach compared to existing monolithic ATP systems, particularly in terms of efficiency, problem-solving capability, and resource utilization?
The decoupled approach offers significant theoretical and practical benefits over existing monolithic ATP systems by enhancing efficiency, problem-solving capability, and resource utilization. By separating high-level reasoning from low-level proof generation, our framework allows a powerful general-purpose LLM to focus solely on generating strategic lemmas, which dramatically reduces the search space for the prover. This targeted decomposition enables the reasoner to leverage its strengths in creative problem solving, leading to more insightful and effective strategies for tackling complex problems, as evidenced by our success in solving 5 IMO problems. Additionally, the prover can operate independently, optimizing its performance on formal verification without being constrained by the reasoning process, thus improving overall resource utilization. This architectural flexibility not only enhances the robustness of the proof generation process, but also allows for iterative refinement of lemmas, which is crucial for addressing challenging mathematical problems effectively.
How was your method validated or tested? Please explain the experimental design, the datasets used, and the benchmarks or metrics for performance that demonstrate the effectiveness of your approach.
Our method was validated through experiments on challenging non-geometry problems from the International Mathematical Olympiad, IMO, spanning the years 2000 to 2024. We specifically focused on this dataset because it represents a high level of complexity and has not been successfully solved by existing open-source automated theorem provers. In our experiments, our framework successfully solved 5 specific IMO problems: IMO 2000 Problem 2, IMO 2005 Problem 3, IMO 2011 Problem 3, IMO 2019 Problem 1, and IMO 2020 Problem 2. The performance of our approach was evaluated based on its ability to generate verified lemmas and construct final proofs, demonstrating a significant improvement over previous methods that struggled with these types of problems. Additionally, we conducted a qualitative analysis comparing our reasoner's strategic decomposition against existing prover-driven approaches, highlighting the superior reasoning quality and structured solution strategies of our decoupled framework.
What limitations or drawbacks does your method have, especially in terms of the prover's ability to verify complex lemmas, and how might these limitations affect its application in real-world theorem proving scenarios?
Our method faces significant limitations primarily due to the prover's inability to verify complex lemmas, which is a critical bottleneck in our pipeline. Many times, while the reasoner successfully identifies plausible high-level strategies, the prover struggles with the complexity of the constituent lemmas, leading to failures in proof verification. This limitation was highlighted in our Oracle experiments, where manually proving these challenging lemmas allowed the framework to solve a greater number of IMO problems, indicating that the prover's theorem proving power directly constrains the overall performance. Additionally, our reasoner tends to excel at systematic decomposition, but lacks the capacity for the creative insights often seen in human mathematicians, which can lead to an ingenuity gap. This gap may hinder the application of our method in real-world theorem proving scenarios, where innovative problem-solving and the ability to tackle complex, nonlinear reasoning are essential for success.